How are you, Dupin? I can't quite see the background behind you, but is that the charges of the standard model?
Yes, and also a list of non-trivial fertility local and non-fertility global anomalies. Anyway. Yes, so you are close now, and you can please feel free to share the screen. Thanks.
Okay. Is it okay? So it says it'll stop your screen sharing. That's okay.
Yes, please.
Okay, you see my slides now?
Yes, great. So we will wait a few more minutes. People usually join a bit later, but
Oops. Be right back.
yeah, I should also. I think we can gradually start. So let me press the recording as well. Welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar series. We are delighted to invite Professor Latham Boyle from Perimeter Institute. He'll be speaking about his series of work with some of them with Niall Turok on cancellations of the vacuum energy and the Weyl anomaly in the standard model and the two-sheeted CPT-symmetric universe. Let me remind the audience, please feel free to ask questions and interact with Latham during the talk, during his talk. when you find the appropriate time. So that is directly welcome lesson. All yours. Please take over. Thank you.
Okay. Oh, sorry, my iPad has logged me out. Okay. Um, so yeah, thank you, Jovan. So I wanted to explain some recent work with by myself and Neil Turok. Um, the main thing I think I want to get across is a new mechanism that we sort of stumbled across to simultaneously cancel both the vacuum energy and the Weyl anomaly in the standard model. Um, uh, we stumbled across it while thinking about a new cosmological model that we've been working on for the past several years and that we've been getting increasingly excited about because we think it increasingly seems to us to give a kind of simpler and more explanatory picture based on a few simple principles of a number of the observed features of our universe as compared with the more popular inflationary model that most cosmologists learn in grad school these days as they are most students are told that this is the right model of the early universe. And so anyway, we've been working on this alternative model, and so I also wanted to explain that because I think it provides some important context for the anomaly cancellation story and also makes the whole line of thought more compelling. Um, uh, uh, and one thing I want to emphasize about the anomaly cancellation story is that other types of anomaly cancellation, cancellation of the gauge and gravitational anomalies in the standard model, are very constraining on the structure of the standard model. Um, they go a long way, as I'll discuss more later, towards restricting what types of fields and what types of representations can appear in the standard model. Um, but all of those anomalies that we normally talk about are all canceled generation by generation in the standard model. So they don't give any insight into why there are three generations of fermions in the standard model. There's this obvious but still unexplained pattern in the standard model, which is that the fermions in the standard model come in three copies of the same strange representation, and each one of those copies is quite constrained by the gauge and gravitational anomaly cancellation in the standard model. But why are there three? Well, the cancellation mechanism that I will talk about turns out to only work for three. So it gives one of the things which is interesting about it is that it gives a new insight into that aspect of things. But okay, so in brief, I'll be let's see. The talk will be divided into three parts. I'll start. It's based on these five papers with Neil Turok, and the first two were also with my former master's student Kieran Finn. The first two were from a couple of years ago, and then the final three are preprints from the past several months. The first part of the talk will basically be about these first two papers, and it will try to introduce how one would get to thinking about this new model of the universe and what it has to say about dark matter and how you can have a CPT-symmetric vacuum in cosmology in this space-time. The second part of the talk will deal with papers 3 and 5 here, which basically fold in when you take account of the fact that our universe observationally appears to be dominated by have a positive vacuum energy, a tiny but positive vacuum energy, which is about to start dominating the energy density of the universe from this point forward. What other implications follow from that? That turns out to sort of add a lot of new elements to the story. And so those first two parts, in a sense, are supposed to give a sense of why this cosmological model is beginning to seem very attractive as a kind of simpler explanation for what's going on for the cosmological observations that we make. And then the third part then will introduce how this anomaly cancellations comes into the story, and how these dimension zero scalar fields that we will use to cancel the anomaly arise in this cosmological model, and how the anomaly cancellation works. I should emphasize that the anomaly cancellation also, the mechanism also works completely independently of this cosmological model. But as I say, I think that the model gives both important background about why one would even think in this direction, and also gives a better motivation to the whole line of thought. Okay. I should also say, by the way, maybe one other thing I wanted to mention is that I am hoping that for this audience, this picture of space-time that we're advocating in this cosmology, where space-time really consists not just of the one sheet we normally think of, but of two neighboring sheets, which are related by a symmetry, as we'll see, and which essentially look indistinguishable except to fermions. I'm hoping that this audience will be interested in that possible picture of space-time and also independently of the anomaly cancellation story, for reasons that I'll get to. Okay, so let me dive in with part one here. This is just introducing the basic idea of this cosmological picture, and briefly what it has to say about dark matter. Simple explanation for dark matter that comes out of it. So here's my cartoon picture of the expanding universe that I want to start off with. So this is time running up the page here. And I have drawn a sort of inverted lampshade to show that the universe is expanding with time. And so we live up here near the top of this figure, and we look back toward the Big Bang with our astronomical instruments. And we can't see all the way back to the Big Bang, but we can see very close. Depending on how you define C, we can see rather directly to only a few 100,000 years after the Big Bang. And then more indirectly, we can see back to a fraction of a second after the Big Bang. And what we see, the remarkable result of cosmological observations over the past few decades, is that, in short, the early universe, as you look back very close to the Big Bang, is extremely simple, much simpler than the late universe we live in. It's really as simple as can be. So this initial surface here that you can see back to a fraction of a second after the Big Bang, what we find is that it's to a first order, it's just a copy of 3D Euclidean space. It's a flat, maximally symmetric and space, I should say, at a given moment in time, and that then on top of that, there's tiny fluctuations. The density and temperature, instead of being completely uniform, completely the same from point to point on that slice, varies, but the variations are about 1 part in 100,000, and they're random, and moreover, they're about the simplest random variations you could think of. They, as far as we can tell, to within our observational limits, they appear to be perfectly Gaussian. They appear to be perfectly adiabatic, which is another simple property. Let me not go into what that technically means. And they appear to be perfectly scale-invariant. Well, they appear to be perfectly scale. They have a 2-point correlation function, which appears to be a perfect power law, to the best we can tell. And moreover, the power of that power law is nearly scale-invariant, to within a few percent. So that's clearly an important clue about the early universe, about what went on at early times. Somehow that as we look back towards the Big Bang, things seem to get simpler and simpler. And the question is, what is that clue trying to tell us? So the traditional and most popular interpretation of what it's trying to tell us, the thing which most people learn in grad school these days, cosmologists anyway, is that is that the clue is trying to tell us that there was an earlier epoch of inflation that stretched the universe out and made the simple early slice that we see. So in this picture, you imagine that there was kind of an earlier big mess, and then there was a period of accelerated expansion that it is argued sort of stretches out the mess, roughly speaking, and turns it into, can take a big mess and turn it into the simple looking initial slice that we see. So that's one possibility, and that's the thing that most people think about these days. But it's important to emphasize that there's no observational evidence. There's no observational or theoretical evidence for this earlier messy epoch. So it's just important to bear in mind that that could just be a figment of our imagination, and removing that mess could be sort of solving a fictitious problem. So we were interested in trying to find a more a cosmological model that takes the observations more at face value. So observations as far back as we can see, which again is very close to the Big Bang, not all the way, but back to a fraction of a second. They seem to be saying that the closer you go to the Big Bang, what you see is a radiation-dominated universe that's getting simpler and simpler the further back you go. So, what if we just try to take that at face value and imagine that really is what observations are trying to tell us, that for some reason, as you go back closer and closer to the Big Bang, the radiation-dominated era just gets, that we actually see, actually just gets simpler and simpler. Where does that line of thought lead?
Naive question. So
yes.
For people who are not familiar with the detail of cosmology established result, how do we know at the beginning of Big Bang the space-time dimension is 3+1?
Well, all we know is that between, so for example, when you say no, we have evidence that from a fraction of a, so there's this calculation of so-called Big Bang nucleosynthesis, which is the calculation you can do where you assume that the universe was a fraction of a second after the Big Bang was already the radiation-dominated 3+1 dimensional Friedmann-Robertson-Walker expanding universe that that we know was in place later. So we know that later, in order to explain the fluctuations in the cosmic microwave background, the observed fluctuations, that those can be very accurately explained by assuming that from, let's say, 1,000 years after the Big Bang onward, or maybe 100 years after the Big Bang onward, that the universe was a 3+1 dimensional expanding universe described by Einstein's theory of gravity plus matter and radiation. And if you extrapolate that backward to a fraction of a second, the radiation becomes completely dominant over the matter. So you would extrapolate that back to a radiation-dominated 3+1 dimensional universe. And the evidence that is still correct, the best evidence, is that when you extrapolate that same cosmological solution backward, all the way to a fraction of a second, you can explain the observed abundances of the various light elements in the periodic table. So the relative abundances of the different isotopes of hydrogen, the different isotopes of helium, the different isotopes of lithium can be explained quantitatively in that picture. And so that provides quite strong evidence that at least back to the fraction of a second needed to explain those quantities, that it's 3+1 dimensional. Earlier than that, we don't. The evidence gets weaker. It's even more circumstantial than that. But back to a kind of fraction, but not a tiny fraction of 1 second. We have quite strong evidence.
How about those people who propose the bouncing universe? Those are still 3+1. In the large space-time dimensions of 3+1.
I think that most usually, yes. There have been other proposals also that are not 3+1. Yeah.
I said the big bounce or the bouncing; those are also 3+1 dimensions. Even before they also before Big Bang, right? On the big bounce.
Well,
later.
so that's what most people have explored all sorts of things. Once you go back to very close to the bang or before, in principle, there's a lot of freedom to speculate about a lot of different things. So most people have considered models where the universe bounces and was still 3+1 dimensional beforehand. That's the most widely considered option. But then there have been other papers about models with other numbers of dimensions, and the Big Bang is maybe related to the collapse of some of those or something like that.
Thank you. Great.
Okay, so sorry, my iPad keeps logging me out when I stop paying attention to it. So great. So as a next step, I'm just going to follow, Penrose's trick that he taught us in the '60s, which is to allow yourself to conformally stretch your space-time diagrams in order to make the causal structure of the boundaries and singularities more transparent. So here I've just taken the previous lampshade and stretched out the bottom. So now that it's supposed to be the same space-time, but I'm just, for convenience, displaying it now as a straight cylinder. Okay, so as I said, I want to try to assume that take the observations at face value and assume that the simplicity that we see, greater and greater simplicity as we go back to the bang, is the real deal. It's just, that's really somehow what observations are trying to tell us is going on. See where that leads. So if that's the case, then we know, to a very good approximation, what the metric was very near the bang. So the metric g mu nu was just basically the flat Minkowski metric eta mu nu times an overall conformal factor, the scale factor a of tau squared. And moreover, the scale factor during the radiation-dominated era is as simple as can be. So it's just proportional to the conformal time tau. So if you extrapolate it back to tau equals 0, there is a singularity, but it's a very special sort of singularity. It's just a conformal singularity, or a Weyl singularity, you might call it, where most of the metric remains completely non-singular, and the only thing that happens, the only singularity, is that the conformal factor in front momentarily passes through 0. But unlike a general singularity in GR, this one is a very, very mild character. There's no ambiguity about how to analytically extend the solution through this singularity. So let's try to do that. So the maximally extended solution then is this sort of extended cylinder where the center here, the dashed line at tau equals 0, is where the bang is. But now in the extended solution, I've allowed tau to run over both positive and negative values. And the first thing you notice about this extended spacetime is that it has a new symmetry, a new isometry, which you didn't notice before, which is this isometry under tau goes to minus tau. So basically, it has a symmetry under just flipping the whole hourglass over. And that's interesting for a number of reasons that we'll get to, but one of them is that it means that the spacetime has a preferred vacuum state for quantum fields living on that spacetime, a preferred CPT-symmetric vacuum state. So, in Minkowski space, in flat spacetime, it's a maximally symmetric spacetime. There's enough symmetry so that there's a unique vacuum state preferred by that symmetry. All inertial observers anywhere in Minkowski space agree on what the vacuum state is, what the state of 0 particles is. But in a general curved spacetime, that's no longer the case. The vacuum famously becomes ambiguous. Different observers at different places in the spacetime will, in general, disagree about what the 0 particle state is. And in particular, that's true in an expanding cosmological spacetime, usually. That an expanding cosmological spacetime doesn't have as much symmetry as Minkowski space, and it doesn't have enough symmetry to determine a preferred vacuum. But it turns out it almost does. An FRW spacetime, a cosmological spacetime, with this extra time reversal symmetry about the bang, does have enough to determine a preferred vacuum state. And so this is kind of the line of thought that led us to think about this idea that maybe CPT symmetry is thought to be a fundamental symmetry of the laws of nature. This is the symmetry where you reflect everything in time, simultaneously reflect it through a spatial mirror, and also swap particles and antiparticles. Uh, and naively, it looks like it's, if you look at the part of the universe after the Big Bang that we normally think of ourselves as living in, it looks like the state of the universe spontaneously violates CPT. Um, but in this extended picture, we see maybe not. And so let's try to let's imagine, let's take the hypothesis that actually the universe does not violate CPT. Okay.
Excuse me.
Yes.
You mean the combination of CPT or the combined CPT, right? Not the individual. The
Exactly.
combined. Yeah, the combined.
Yeah. So here I just briefly describe kind of a bit more about what I mean about that choosing a preferred vacuum state. So imagine I have a quantum field now living on that extended space-time. So for example, here's a Dirac spinor, and I've decomposed it into the way I normally do. The way I normally quantize a field on curved spacetime is I decompose it into a complete basis of solutions of its wave equation, in this case the Dirac equation. And I split those solutions into the positive frequency solutions, which I've called psi here, and then the corresponding negative frequency solutions, which in the Dirac equation are the charge conjugate solutions psi c. And then I promote the coefficients in front of the positive frequency solutions, these a's. I promote those to annihilation operators of the particles, and the coefficients in front of the negative frequency solutions I promote to creation operators of the corresponding antiparticles. And again, the issue now is that it's crucial that I know how to split the solutions into positive and negative frequency in this process. And the issue is that, okay, in flat space, there's no ambiguity about how to do that. All inertial observers agree about which solutions of the Dirac equation have positive frequency and which ones have negative frequency. But in curved spacetime, it becomes ambiguous. Different observers disagree. And so in particular, a late time observer, an observer up here towards the top of the cylinder, long after the bang, they would define a certain subset of the solutions to have positive frequency. So I'll call their positive frequency solutions psi plus. And so when they do this decomposition, they would define certain annihilation operators A plus and B plus, and the state, they would define the vacuum to be the state 0 plus annihilated by them. But an early time observer, long before the bang, would have a different set of solutions, a different subset of the solutions that they would define as the negative frequency solutions, so as the positive frequency solutions. So psi minus are their positive frequency solutions. And so their corresponding coefficients are some different operators, A minus and B minus, and the vacuum that they define, the state annihilated by A minus and B minus, is a different state, 0 minus. So 0 minus and 0 plus are two inequivalent states in this space-time, and they are exchanged, it turns out, by CPT-symmetry. And so neither of them can be CPT-invariant. You can define a CPT-symmetric state, a CPT-invariant state, by instead taking positive frequency solutions psi 0, which satisfy an extra condition, which roughly is that psi 0 at time t is equal to the charge conjugate solution psi 0c at time minus t. And then the coefficients define a vacuum state 0 sub 0, or 0 CPT, which is invariant under CPT. Okay, so what are the observational implications of this? So if the universe is really in the we can, since ultimately these are all just different bases for the Dirac equation, we can take these CPT-symmetric solutions, the basis solutions, and decompose them in terms of the basis that a late time observer like us would use, and these the coefficients in the coefficients here are the so-called Bogoliubov coefficients, A and alpha and beta. And now, if we ask, if we imagine that the universe is really in the CPT-symmetric vacuum state, and we ask what is the expected number of particles in the universe according to a late time observer like us. So we calculate the expectation value of our late time number operator with respect to the CPT-symmetric vacuum state. then that is given by the square of this Bogoliubov beta coefficient. And it's given by some non-zero answer. The details are not important, but anyway, you can calculate the answer. But the bottom line is that what this is saying physically is that, according to if the universe is really in the CPT-symmetric state, then according to a late time observer like you or I, we interpret the universe as being full of a non-zero bath of particles, which are sort of emerging from the early universe into the late universe. And it's very analogous to Hawking radiation. Hawking radiation is this famous effect where the black hole is really in one state, but because space-time is curved, an observer far away from the black hole defines a different vacuum state. So according to them, they interpret a non-zero flux of particles emerging from the hole. Similarly here, the universe is really in the CPT-symmetric vacuum state, but an observer far from the bang naturally defines a different vacuum state. So according to them, the universe appears to have a non-zero flux of particles coming out from the bang. And so we can try to apply this idea now to the standard model of particle physics more specifically. So here I'm just briefly reminding you what's in the standard model. So the top line here are the bosonic fields. There's a gauge field for each of the three different gauge groups in the standard model, SU3, SU2, and U1. And then there's the Higgs field, the Higgs doublet. And then we have the fermions. So there's the quarks. There's a left-handed down quark, left-handed up quark, right-handed down, right-handed up. Those come in three colors. And then there's the corresponding lepton fields. There's a left-handed lepton, left-handed neutrino, right-handed electron. And in the minimal standard model that people focused on, let's say, up until the late 90s, that's all there is. And in that model, there's no longer any possible dark matter candidate. I mean, there's just no particles left in that theory that are stable and that haven't been detected, but haven't been detected yet. So there's no remaining stable dark particles in that theory. But ever since the observation of neutrino oscillations and neutrino masses in the late 1990s, it's been common to imagine that the standard model also includes a right-handed neutrino, which gives the simplest renormalizable explanation for the observed neutrino oscillations. So let's assume that there is such a particle in addition. Oh, and by the way, I forgot to mention, so in addition to the fermions that I described, again, they come in three copies. There are so-called three generations of this pattern of fermions. So there's really three of these right-handed neutrinos, and they are special among the standard model particles because they're the only fermions they're the only particles that don't talk to any of the gauge forces. So they're darker than the rest of the particles in the standard model. Now we know from neutrino oscillation experiments that two of these three right-handed neutrinos have to be unstable. So they would have decayed in the very early universe, and that's okay. Actually, their decay turns out to give a very elegant explanation for where the observed excess of matter over antimatter in the universe comes from, called leptogenesis. But the third of these right-handed neutrinos still can be stable. And it's compatible with everything we know that it is stable. And that is really the last possible dark matter candidate in the standard model. If you don't want to go beyond the standard model, that's your only hope. So let's try to make use of that. See if this combining. Let's see if the CPT symmetric idea can resurrect that last standard model dark matter candidate, make it into a good one. So we have our one stable neutrino. One stable right-handed neutrino. It turns out that it can be stabilized in the standard model in a very natural way. You can just take the Lagrangian if you just demand the Lagrangian as invariant under that neutrino goes to minus itself, that stabilizes it. But at the same time, that same symmetry also decouples it from everything else in the standard model. So it no longer talks to, it already didn't talk to the gauge fields. Now it also doesn't talk to the Higgs or any of the other fermions in the standard model. So it's really completely dark. It only talks to gravity now. It's just a free particle living on the background spacetime. We can apply exactly the calculation that I showed on the previous slide. So we can say if the fields in universe are really in the CPT-symmetric vacuum state, and in particular this neutrino is in its CPT-symmetric vacuum state, now we can ask what is the abundance of it that a late time observer like you or I would say is present in the universe. So in particular, you can calculate this dimensionless ratio of the number density of this dark matter neutrino to the entropy density of the radiation. And the details are not important here, but it's given by some expression which depends on the mass of this neutrino, this dark matter particle, divided by the Planck mass to the 3/2 power. And so if you ask, so it depends on the mass of the particle, how much of it gets produced in this way. And you can ask, what does its mass have to be in order for its abundance to match the observed abundance of dark matter in the universe today? And it turns out it matches the dark matter abundance if its mass is 4.8 times 10 to the 8 GeV, which is about 1 billion times as heavy as a proton. So we interpret in this, so we're trying to say that this a first advantage of this CPT-symmetric perspective, the CPT-symmetric model, is that it gives a very elegant and precise explanation for the dark matter. It's just the last remaining candidate particle in the standard model, and we interpret the observed abundance of the dark matter as nothing but a measurement of the mass of that particle. Juven, did you have a question?
Oh yes. Let me just make sure. The Z2 symmetry you write on the top is the fermion parity symmetry.
No. This is a symmetry that only applies to this field. It's just saying that under this that the Lagrangian this is a Weyl spinor field here that appears in the Lagrangian, one of the standard model Weyl spinors, and I'm just demanding that for that field and that field alone, that the Lagrangian
no problem.
is apparently invariant under it goes to minus itself.
Okay, fine. But it's not for other fermions, but it's a fermion parity, fermion parity for this fermion. For this,
I guess you could say that. Yeah.
Yeah. But then yes, and that's certainly different from the CPT symmetry you are saying earlier, which is also a Z2, right? That's a different.
I think it's not the fermion parity here. It's something like you can think it as a Z2 gauge field. The neutrino on the right-hand neutrino carry this Z2 gauge charge 1.
But here not necessary gauge, right?
It can also be a global symmetry, yeah. But if it's a global symmetry, then it carry this global charge. It's just ordinary Z2 symmetry, has nothing to do with the fermion parity.
Yes, it's not a fermion parity for the whole system. Yeah, I will just try to make sure. But I say these are different from the CPT symmetry.
Yes, that's also true. Yeah.
Yeah, and so I'm not sure. So how do you tie this together with the earlier CPT things? I'm not sure I follow this.
They're two different symmetries. So you're absolutely right. They're not a priori tied together in any way. The CPT symmetry seems to be suggested just by when you look at the maximal analytic extension of the space-time that we seem to see in the early universe. This other symmetry just has to be there. It apparently either is exact or to a very good approximation present if you want the last remaining possible dark matter candidate in the standard model to actually be a stable dark particle. It's what is needed. It's not that it's justified by CPT symmetry. It's just observationally, it apparently is there for some reason if that neutrino is. I mean, we see dark matter. The question is, what is it? Usually you assume, oh, I have to go beyond the observed particles in the standard model. But if you want to make do with just the standard model, you need this guy to be stable. And this is the symmetry that stabilizes it. So it could just be that its couplings to the Higgs are very small. Really, the effect of this is to set to zero its couplings to the Higgs, which would otherwise allow it to decay. So really what I'm trying to say is that its couplings to the Higgs are apparently so small that it can live for a cosmological time. But it appears that the most elegant way to do that is to just demand that the Lagrangian has this extra symmetry for some reason.
Let me try to understand what exactly is on the story. So you have this Z2 symmetry X on the right-hand neutrino, maybe on each of the generation.
No, only on this one. Only on this one.
Okay, for just one generation. And then there's also the CPT symmetry, which also acts on fermion, which will send fermion to its anti-particle side to side star, but also flip the space-time coordinate tx to minus t minus x. And possibly also flip, I think, either left hand or right hand to minus sign. But the standard CPT defined on the biospinor will be that. And these are distinct from the Z2 you talk about. And I suppose you are trying to refer to the neutrino. There's the light states, three of them, maybe from some mass eigen basis. You have a 3 light one, but the 3 heavy one for the left-handed and right-handed. Mm-hmm. And you try to refer to those heavy state is some sort of a stable dark matter candidate. Is that the way
yes.
to think about it?
Yes. Oh, sorry.
So how, can you fill in more what a logical gap I didn't state?
Yes. So when you have right-handed neutrinos in the standard model, then there's always 6. In general, there's 6 mass eigenstates, and typically 3 of them are heavy, and 3 of them are the ones we observe. They're very light. And so the idea here is that this is all true independent of the CPT symmetry idea. This is just a fact about this. This is just now some facts about the standard model when you include right-handed neutrinos. So there's these 3 heavy mass eigenstates, 3 light mass eigenstates, which are neutrino mass eigenstates. And the idea is that we know from neutrino oscillation experiments that 2 of the heavy eigenstates are unstable and will decay in the very early universe. So those I want to use their decay to explain the observed asymmetry between matter and antimatter. But one of those could still be stable. One of those 3 heavy guys could still be stable. And I'm saying that's the last remaining possible dark matter candidate in this theory. So I want to go to the trouble of trying to make sure that it is stable. And so, again, independent of the CPT symmetry idea, just in the standard model period, you can make that particle stable. Making that particle stable is essentially equivalent to saying that this symmetry is either exact or a very good approximate symmetry of the Lagrangian. And then the thing which CPT symmetry adds to the story is that, see, normally once you make this particle stable in the standard model, it's completely decoupled from the rest of the particles in the standard model. It only talks to gravity. You might ask, how do you actually make it? Why would the universe be full of it? Why we observe a certain non-zero abundance of dark matter, but this particle would have never been in any contact with a thermal bath in the early universe. So how did it get produced in the first place in the abundance that we observe? The CPT symmetry story adds an answer to that question, that if the universe is really in the CPT-symmetric vacuum and the late universe is inequivalent from that, then inevitably, even if it only talks to gravity, we still see a non-zero abundance of it because of a kind of Hawking radiation-like effect that causes it to radiate from the early universe. A purely gravitational effect. Does that help?
Yes. So the Z2 symmetry on the slides try to make it stable for the lightest heavy one.
Exactly.
And the CPT symmetries make it abundant at the beginning of the universe.
Exactly.
And how about the energy the analysis of the numerics here? How do you get those numbers?
Where does this number come from?
Yes.
So, well, it's a little bit more calculation than I was going to go into. But the rough sketch is that, so this, I was saying you can get this dimensionless ratio, which is the number density of these dark matter particles over the radiation density, the entropy density of the radiation, and that turns out to be a conserved quantity between the early universe and today. So once you know that quantity, you can predict we know the entropy density of the radiation in the universe today. And so once you know this ratio, you can predict the number density of the dark matter particles in the universe today. And so the only thing you need to convert that to the energy density of dark matter in the universe today, which is what we actually observe, is the mass of the dark matter particle. So you can infer the mass of the dark matter particle by comparing that calculated number density to the observed mass density.
And this will be the mass for the lightest heavy neutrino, presumably get a mass from the Marana mass type of term.
Yes, exactly.
You'll say, okay, and you will say it will be 10 to the 8 GeV. Let's say something. No problem.
Exactly. That's what it has to be. That's what we're measuring that. We don't have an independent argument that it should be that. It's just that that's what it's measured to be in this picture when we measure the observed dark matter abundance.
So this can be a prediction.
Yes.
The mass. Okay.
Yes, exactly. So I was just going to say. So I'll now say. So the mass is a prediction. Unfortunately, that it's a hard prediction to directly test that prediction for the mass because this particle is so dark. However, it could be imperfectly dark, so it could decay, and then you could see it decay into two particles at half that energy. But I think that's probably wishful thinking. I think it's probably completely dark and stable. But there's an indirect way there's several indirect ways to predictions that can be tested in the near future, that any of which, if it turns out to be wrong, will rule out this scenario. So one of them is that the 3 light neutrinos, again, what we observe from neutrino oscillation experiments is that they have a certain pattern of mass differences, but we don't know what the overall gap between how much the overall pattern of mass differences is offset from 0. We don't know, in other words, the mass of the lightest of the 3 light neutrinos. But in our scenario, the lightest has to be 0. So the first thing is that we can predict what the sum of the 3 light neutrinos is. It has to be either 0.06 eV or 0.12 eV, the minimum possible value consistent with neutrino oscillation experiments. And this cosmology experiments are measuring this in the coming 5 years. So we're basically, they should measure this value to plus or minus 20%. So within the coming 5 years. So either they will get one of these two values, or this idea is not correct. A little bit more in the future, we also end up making a very specific prediction for the rate of neutrinoless double beta decay. That's a process that hasn't been observed yet, but if this theory is right, there's a small but non-zero rate that we predict for the neutrinoless double beta decay that can be ruled out. So a second prediction is that the dark matter should be completely cold, ultra cold, meaning that it has essentially no observable velocity dispersion. That's something that cosmologists also test in a lot of different ways. There are a lot of competing dark matter models, warm dark matter, fuzzy dark matter, which would differ from cold dark matter observationally. And if any of those end up being favored over cold dark matter, again, this model is ruled out. And then the final thing is that it turns out that for the same sort of calculation that we did for the neutrinos actually also can be applied for the gravitons. So the prediction is that there are no primordial gravitational waves. This is in contradiction. This differs from the predictions from inflation, where many of the simplest and most compelling inflation models do predict a non-zero gravitational wave, primordial gravitational wave spectrum, although there's other models that don't. In general, an issue with inflation is that often there's models that predict one thing and other models that predict the opposite thing. But in any case, our theory predicts that there should be no primordial gravitational waves, so again, if observations which are actively pursuing those by looking for the polarization in the cosmic microwave background, or with gravitational wave detectors, if they detect primordial gravitational waves, again, that rules us out.
Sorry, question.
Yes.
May I? First of all, the scale that you predict for the heavy, but the lightest neutrino with this 10 to the 8 GeV scale is about it's much lighter than the Gauss scale people usually put, right? So that's probably a distinct feature of your prediction. Another thing is that you also predict one of the neutrino is massless. I suppose one of the eigenbases diagonalized from the left-hand neutrinos. Can you say again why? Probably you say it, but I didn't get that point.
No, I didn't explain why, but I can explain here. Let me see. So I guess I'll write on this slide. So the idea is that right-handed neutrinos, they appear in two different places in the standard model. There's on the one hand there's a Yukawa coupling of the left-handed lepton to the Higgs to the right-handed neutrino, and there's a kind of one Yukawa matrix that appears here, and then there's an explicit mass term that you can Majorana mass term that you can only write down for right-handed neutrinos, which is something like this. Okay, and then so this is a 3x3 dimensionless matrix, and this is a 3x3 matrix with dimensions of mass, and then the Higgs gets the Vev, which has dimensions of mass v. So the way the seesaw mechanism works is that the masses of the light neutrinos, when you calculate them in terms of these quantities, they end up having masses which are like v squared over they end up having masses v squared times y m inverse y transpose. And so it turns out the reason that one of the light neutrinos is massless is because it turns out that the symmetry that stabilizes one of the three right-handed neutrinos has the effect of killing one of the columns of this 3x3 matrix. So one of the columns of this matrix becomes 0. So y has determinant 0. But that means that the light neutrino mass matrix here is a product of three matrices, y, m inverse, and y, where y has determinant 0. So this light neutrino matrix also has determinant 0. So that's telling you that one of the light mass eigenvalues is 0.
But why one of the eigenvalues is 0?
So what I'm saying is that if y, the symmetry nu right goes to minus nu right, that had the effect of killing one whole column of this matrix y. So that's what you had to do. You had to kill all of the right-handed neutrinos. The stable right-handed neutrino, you have to shut off all of its Yukawa couplings to the Higgs. Otherwise, if any of them are present, it can decay.
I see. Yeah.
So then y has determinant 0. But then this mass matrix has determinant 0, and so one of the eigenvalues is 0.
Yeah, so you're saying that one of the lightest heavy neutrino of 10 to the 8 some scale that GeV is the mass is solely from the Majorana mass.
Exactly.
Not mixed with part of Higgs.
Exactly. That turns out to be equivalent to the condition that it's stable.
And is that stability just require that suppose you only have a SM gauge forces without any other gauge forces, like does other possible gut structure will make it decay? I don't know. Yeah, I just asking.
You're saying if you extended the standard model, would there be other ways to make it decay?
Yes, just a comment anyway.
I'm probably yeah.
Okay.
Yeah, if you add more fields, then you could still find ways to make it decay. I think so.
Yeah.
Okay, great. Well, let's see. Maybe I'll be a little bit faster about this part because I want to get to the anomaly part. Anyway, the discussion is great, but I'm recalibrating my time here. Okay, so far I've tried to explain why I've been talking about looking back toward the Bang and analytically continuing the solution through the Bang, space-time through the past through the Bang, and the implications of that. now I want to make use of the other thing we observe about seem to see about the other end of our space-time, the future, which is that it appears to be beginning to accelerate as if there is a positive cosmological constant. And so it looks like the future will be dominated by a positive cosmological constant. And when you fold that into this extended space-time picture, that has a number of additional consequences. It gives a nice new explanation for the observed arrow of time, the fact that entropy seems to increase as you get further from the Big Bang. And then it gives a way to calculate the gravitational entropy of our space-time, which in turn gives a new explanation for why the observed universe appears to be very homogeneous, meaning invariant under translations in space, isotropic, meaning invariant under spatial rotations, and flat. Spatial sections appear to be, at a given time, appear to be flat. Okay, so what's the idea? So here I've written down the Friedmann equation, the one sort of Einstein equation that applies to a cosmological space-time if you neglect perturbations for the moment. Here I've included the radiation that dominates the universe at early times and the cosmological constant that dominates the universe at late times. And then I've also included this curvature term, where kappa equals 0 plus 1 or minus 1 if the universe is flat or closed up into a three-sphere, or if spatial sections have negative curvature, if they're hyperboloids. This is the simplest modeled universe that has the right asymptotic behavior at early times, dominated by radiation, and late times, dominated by cosmological constant. I've left out an important third term in this Friedmann equation, which is the contribution coming from non-relativistic matter, like you and I, and the stars and galaxies in the universe today, and the dark matter. So for the moment, I've just left that out so I can analytically solve the equation, but then I'll add it back in a few slides. So it's helpful to do it in this order. So if I take this Friedmann equation, well, then I can exactly solve it. The solution is given by A of, oh, sorry, I switched notation. Eta now is I was previously calling the conformal time tau, and now henceforth I'm calling it eta. Sorry about that. So the solution of this equation is that the scale factor A of eta is described by this Jacobi elliptic function Sn. So here this is alpha and beta and m are just constants. The details are not important, but the bottom line is that this function depends on the conformal time eta. And it's a Jacobi elliptic function, which is this beautiful analytic function that has this property that it's doubly periodic in the complex plane. So it has two different directions in which it's periodic, and so it forms a kind of periodic tiling of the complex plane. So here I've drawn the solution along the real eta axis, and here's the physically relevant solution is the solid blue line here. So this is the usual part of the solution that we think about as the universe starts from the bang at A equals 0, and then eventually A diverges. That's the future boundary of space-time. And you notice that in terms of the conformal time coordinate, that there's only a finite difference in conformal time between the Big Bang and the future boundary where the scale factor diverges to infinity. And in the previous section, we were talking about extending the solution to negative values back through the bang. And now here I've just also extended it over all time, and we see it just repeats. It goes through a pole at a finite eta here, and then just forms a periodically repeating pattern. So if I draw a space-time diagram, then if this is the sort of spatial three-sphere of the universe, then what happens is that we have the bang down here, and the universe expands. A gets bigger and bigger and diverges to positive infinity up here, and then if we go around the pole, it comes back from minus infinity back to 0, and just circles around here. That's the reflection of the periodicity of this solution along the real eta axis. So we get this picture along the real eta axis of the universe as a two-sheeted cylinder where the inner and outer sheets of space-time, normally we just think of ourselves as living on the outer sheet of the space-time, but if we really take this analytic continuation seriously, it's saying that the cylinder has two sheets which are related by a symmetry. Neighboring points on the inner and outer sheets are swapped by an isometry of the space-time. And the only difference is that A goes to minus A. The scale factor goes to minus A as you go between the inner and outer sheet, which means the metric, which only depends on A squared, doesn't change. It's completely symmetric, but the fermions feel the square root of the metric. They feel the tetrad. And so for fermions, there is a difference between the two sheets. So now I want to give some reasons to take seriously this analytic extension. Some bits of evidence that this is not just an artifact, but that this really seems to be. Yes.
Excuse me. Sorry, I'm not sure I follow what you were saying earlier about the two sheet. So what is the standard? What is the standard picture, and what's the new ingredient you add to this? I think I cannot. I didn't distinguish what is known and what is new.
So this. So I think this picture where we write down the solution and consider its full analytic extension as opposed to just restricting to the positive part of A. So normally if people consider solutions of the Friedmann equation, they restrict to the part of the solution along the real time axis and where A is non-negative, is positive. Okay, but we are going to observe, already in the previous part of the talk we were observing, but then I'm going to observe in a number of other ways that now if we really consider the full maximal analytic extension of the space-time, including along the real eta axis, the parts where A is positive and the parts where A is negative, then first of all, we notice that there's new symmetries of the extended spacetime that map the parts where it's positive to the parts where it's negative, and that the more we take those symmetries seriously, the more things we turn out to explain about the more observed facts about the universe turn out to have nice explanations. So I'm kind of trying to. So the new thing is to take this full analytic extension seriously, and then notice that it has a bunch of observable or explanatory consequences about the universe that hadn't been noticed before. So that's the new part.
And is that CPT symmetry or is not? Which is symmetry?
It's very closely related. So
which symmetry here it is? Just to make sure.
So far what I'm discussing is really a classical isometry that the metric at a given point on the outer side of the cylinder, on the outer sheet of the cylinder, maps that it's an isometry of the space-time to map the outer sheet to the inner sheet. So one of the things I will do is I will demand that is not an artifact, that even when we introduce matter fields and when we introduce perturbations in the metric, so it's no longer just the perfect FRW cosmological symmetric space-time, even when it includes density perturbations and gravitational waves, etc. I want to demand that fact, that structure, that there's two sheets that are related by an isometry, that remains true. That will turn out to have a bunch of consequences. But one of the consequences is the thing that I mentioned before, that if you have a space-time that has that extra symmetry, then then there's the preferred vacuum on that space-time, which is CPT-symmetric. So one consequence of the fact that the space-time has this extra symmetry is that there is a is that when I consider quantum fields on that space-time, I can demand that the vacuum be invariant under that symmetry.
Yes,
and
but
the CPT-symmetric. But it's not the same. It's not. It's the actual symmetry of the space-time is not CPT symmetry. It's a different. I mean, it's gonna turn out to be a reflection symmetry around the bang here. It's gonna be like the bang is a mirror.
Okay. Well, I can make I don't think it's the same thing, but I can make a few comments. For example, if we have a fermion parity, a Z2F, then the space-time structure, you just consider the rotational symmetry of the space, or possibly the Lorentz boost. You can consider the SO 3,1 or D,1, but the fermion will give you a extension by fermion parity to a double cover spin group. But that's a different symmetry. That's a fermion parity symmetry. And here, I think the symmetry you mean is the reflection just along the Big Bang. Is that what you say?
That is the symmetry which exactly that's the symmetry which is which when you extend it to perturbations in matter fields living on the space-time seems to explain a lot about our universe. That's right. On the other hand, then there is but then the dark matter story that I was mentioning is really about the CPT symmetry of the vacuum, which is a different story. That's a slightly different story about how you split up the mode functions into positive and negative frequency. It's a related but not the identical story. It's more of a consequence of this. It's a story you can tell because the underlying space-time is assumed to have this extra mirror-like symmetry. Well, what?
Yes, yeah. To me, they are different things. But if you see them related, maybe either I didn't get it, or maybe we can discuss later. They seem to be different.
They are
Yeah,
different.
they are different. Yeah, but I don't see
different things. So in other words, you could have a space-time that has this symmetry, this two-sheet symmetry under mirror reflection, without having the vacuum state on that, without choosing the CPT-symmetric vacuum state on that space-time. However, because the space-time has this mirror symmetry, there is a preferred vacuum state on the space-time that respects that symmetry, and that is the CPT-symmetric vacuum state. That I believe is the story.
But sorry, I'm confused. I think the symmetry you mean here is just a solution, a symmetry of this equation such that you flip a to minus a, or is there more than that?
So the symmetry here is going to be maybe let me describe it more in a moment. But it's demanding at the level of the background metric. It's just a goes to minus a. At the level of the perturbations of the metric, or at the matter fields living on space-time, it's more than that. It's the demand that the whole configuration be symmetric under reflection through the Big Bang.
But
it's a kind of mirror-like boundary.
Why do you need to take the two things as a two sheet? Seems like they could be different side of the solution on the parameter of eta. Is that right? So they could just be different set of. Why do you regard this as a two sheet? Why don't they just separate in a parameter of eta in two different point of eta? Maybe also there's a map between maybe eta to minus eta some way, some kind of map between a of eta. So why the two solutions need to be covered? It's also not quite double covered, right? Yes.
It's so this is let me get to the next two slides,
okay,
which is
no
really
problem, sure.
about explaining this point. So that's a good question, and so let me so I'll get to it on the next slide, but let me first say one other thing. So I'm beginning by trying first. So I want to again accumulate for evidence that you should consider this and you should take seriously this analytic extension of the spacetime, and then the question about why Juven, your question is on the next slide. So here's another point that another reason to take seriously the analytic extension. I guess the one reason we've seen already has to do with that it gives a nice explanation for the dark matter. Here I want to now consider the analytic extension into the complex eta plane. As I mentioned before, this solution for the scale factor A is now a doubly periodic function in the complex eta plane. So you see it forms this sort of tiling of the plane. So if I calculate the physical time t from the conformal time eta, well, that's the physical time is as usual the integral of the scale factor times d eta. But now so in this picture, the blue x's are where the function has a simple 0, and the white circles are where the function has a pole, and the poles can have either negative or positive residue, which I've marked with a minus or a plus. Because it has poles, the value of this integral depends on how the contour goes around those poles. So for example, if I want to calculate the physical time between this green dot and this green dot, well, one path would just go straight along the real axis, but another path would circle around this pole. Those paths will in general differ by an integer multiple of this delta t, which is a purely imaginary constant shift, which is 2 pi I over the Hubble expansion rate in the far future, the so-called, or 2 pi I times the so-called de Sitter radius. But then a famous fact is that systems in which the time is periodic in the imaginary direction, or which the time is identified under a shift in the imaginary direction, is equivalent to a statistical system in thermal equilibrium at some temperature, and the temperature can be read off once you know the shift in the imaginary time direction. And so in this case, you can read off that the temperature of this spacetime is the de Sitter Hubble rate divided by 2 pi, which is exactly the standard answer for de Sitter space, the empty space with a positive cosmological constant. But now we've found that it extends to this much more general class of spacetimes, cosmological spacetimes that include radiation and include positive or negative or zero curvature, in addition to a positive cosmological constant. Now, let's add matter back onto the spacetime. So this, Juven, will hopefully help clarify the question you were asking about a moment ago. So the simplest matter field I can add on the spacetime is just a massive scalar field, which obeys an equation of motion in curved spacetime like this. But now, again, what I want to do is I want to interpret the fact that the solution for the scale factor has these two sheets related by a goes to minus a. I want to interpret that as not just an artifact of the analytic extension, but as a hint about the way the universe really is. And so I want that fact to be preserved when I add matter fields to the spacetime. And so in order to do that, the solutions of the matter fields that I consider have to respect that symmetry. They have to either be sort of even or odd as I follow them from one sheet to the other. An interesting thing is that, well, I can now get if I know the value of the scalar field on the inner sheet, let's say, I can get to the value on the outer sheet in two ways. I can use the assumed symmetry just to jump directly from the inner sheet to the outer sheet. But alternatively, I find that the solutions like the solution for the metric, are analytic at the bang, so I can also just analytically extend the solution around the bottom and back up to the point on the outer sheet. And consistency between those two ends up forcing me to take a mirror-like boundary condition on the Big Bang, either Dirichlet or Neumann boundary conditions for the scalar field, depending on whether the scalar field is even or odd as I jump from the inner sheet to the outer sheet. On the other hand, if I try to follow the solution up toward the future boundary, the de Sitter boundary, it turns out there's always a essential singularity up here, so I can't follow it over the top here. So there's no corresponding boundary condition up at the top. So I want to say that gives a so the fact that it's analytic at the bang means that we get reflecting boundary conditions down at the bang. Non-analytic at the top means no such boundary conditions at the top, and that gives a simple new explanation for the observed thermodynamic arrow of time. The observed fact is that the entropy of our universe grows as we get further from the Big Bang. And it's long been argued, for example, by Penrose, that must mean that something set the universe to a very special point in phase space at the beginning, and that then it's been gradually working its way into a less special place in phase space as the universe evolves, which is why the entropy has been growing. But the question is, what sets the special initial condition at the Big Bang, and why is it there and not in the future? What breaks the time asymmetry? And here we have a new explanation for that we find that just the symmetry plus analyticity implies that there is a restrictive boundary condition at this end of space-time where the radiation dominates. There's this mirror-like boundary condition which pins us to a very special point in phase space. But at the top, at the future end boundary of space-time, there's no corresponding boundary condition, and so that seems to be a simple answer to the question. Now I've mentioned I've now applied this argument to a scalar field, but let's apply it now. The same sort of argument can be applied to the tetrad, the square root of the metric field, which is the thing that fermions actually couple to in curved spacetime. So now instead of just assuming a symmetric cosmological spacetime for the tetrad, let's allow all the different kinds of perturbations that can be present. There can be so now if we apply the same argument to the tetrad, it turns out that the symmetry condition at the bang rules out primordial vector perturbations or primordial vorticity, which is good because we see that there's no primordial vorticity. And then for the primordial scalar perturbations, or in other words, density perturbations, and the primordial tensor perturbations, or in other words, gravitational wave perturbations, the symmetry turns out to kill the so-called decaying mode solutions, which, okay, for the tensors, for the gravitational waves, that's an academic point, since I already argued that those are not present. But for the scalars, that turns out to be exactly what you need to explain the ringing pattern. This is this famous picture of the power spectrum of the cosmic microwave background, where you see that at certain sizes on the sky there's a lot of ringing, and at certain sizes on the sky there's less power in the temperature fluctuations in the cosmic microwave background. And that's because that's exactly interpretable as this statement that why there are peaks and valleys here, and where the peaks and valleys are completely explained by the fact that there are no decaying mode scalar perturbations. So that's another thing. That's another point which agrees with observations. So this is these two slides, Juven, were supposed to be showing that the idea that if you take this hint, if you interpret this hint about analytically extending the background space-time to be still valid when you include matter fields and perturbations in the metric. The thing which you're demanding really, the thing which when you demand it, demanding that the inner and outer sheets remain in lockstep with one another, apart from the fact that the tetrad is flipped on one sheet relative to the other, appears to be the right condition because it appears to explain a bunch of things about the observed facts about the early universe. Does that?
Well, I have to think more. I need to think more to understand the point. But thank you. I need to think. Not sure what I get it.
Okay, I'm happy to discuss more later. If it's okay, I'll maybe go ahead for now. Just
please,
I
please,
want to make sure
please.
to get you the. I see. I'm sensitive to the fact I only have 10 minutes
Yeah,
left,
please.
and I want to get to the punchline here.
Yeah, take your time. It's okay. Don't worry about it.
So just the last point in part 2 here, and then part 3 will be. Fortunately, the punchline is rather simple, so it'll be quick. The last point in part 2 here is that the final and maybe most interesting bit of evidence or most exciting bit of evidence that we should take this analytically extended space-time seriously is that, so as I mentioned before, the solution for the scale factor is doubly periodic. It's not only so far we've mostly been focusing on its periodicity as we go along the real time axis, which is what makes us go around and around between the two sheets and the two-sheeted cylinder picture. But now it's also periodic in the imaginary time direction, and I already mentioned that we use that to infer the temperature of the space-time as the de Sitter temperature, but we can also use it to calculate the entropy of the space-time by calculating the integral of the action along that imaginary direction, along one period. So here I've drawn a fundamental domain in the periodic pattern in the complex plane for the scale factor, and so here I've if I identify the left and right sides here and the top and bottom, I get this torus, and I want to calculate the action around this red loop, and it turns out to be a topological invariant, so I can displace it to any other topologically equivalent loop, and the action computed along that direction is interpretable as the entropy of the space-time. And to make a long story short, the result is that this was in a paper from January that Neil and I wrote, that the space-time of highest entropy is the one that is the flattest, is the spatially flattest. So we observe that we're in a universe that it could have been a cosmological space-time that's homogeneous and isotropic could be either spatially flat or spatially positively curved or spatially negatively curved. Well, we appear to be in one that's spatially flat. We observe that we're in one that's very, very close to spatially flat. We've not detected any positive or negative curvature. So that's the so-called flatness problem. And we propose a new explanation for that, which is that that is the configuration of highest entropy. And moreover, if you now add we also show that if you add scalar and tensor perturbations, if you perturb away from the perfectly homogeneous and isotropic solution to make it inhomogeneous or anisotropic, that costs entropy in the same calculation. So it's also the so-called homogeneity and isotropy problems in cosmology are why does the universe appear to be homogeneous and isotropic, invariant under spatial translations or under spatial rotations. At least it's not so visible in the universe today. It's only statistically true in the universe today, but at early times it was very accurately actually true. So again, we're pointing out that if you take this analytically extended spacetime seriously, that is the configuration of highest entropy. Okay, fine. So that was all. Took much longer than I expected, but that was all the introduction to the cosmological introduction to why this model we think is an improvement on the sort of more conventional cosmological picture of the early universe based on inflation. now I want to explain how in the process of thinking about this, we came across this new anomaly cancellation mechanism in the standard model using dimension zero scalar fields. Okay, so what's the idea? So, as you know, symmetries can be global or local symmetries. Normally, and then those symmetries can have anomalies in principle, meaning that they could be symmetries at the classical level, symmetries invariances of the action, but maybe not symmetries of at the quantum level, no longer symmetries of the path integral. Normally, it's fine for a global symmetry to have an anomaly, and of course we know there are real global symmetries in nature that are anomalous. But it's normally thought that gauge symmetries, local symmetries, like the symmetries of gauge invariance and diffeomorphism invariance and gravity, should be anomaly free. And indeed, in the standard model, those symmetries are anomaly free. So here I've taken a picture from Peskin and Schroeder where he writes down all the different triangle diagrams that have to each separately vanish in order for all of the gauge and gravitational anomalies in the standard model to vanish. And they do all vanish. And the vanishing is quite non-trivial. So for example, here I've shown the calculation for the U1 cubed anomaly, that triangle that has to vanish. And so it ends up being quite non-trivial how it vanishes. There's this sum of these various weird numbers that all have to vanish, and they do all vanish in the standard model. So that's this first diagram. But then there's for each of these diagrams, you need a corresponding sum of numbers to vanish, and they do in the standard model, and that's very restrictive. That tells you a lot about the standard model, as I was mentioning before. So for example, there's different ways to say it, but one way to say it is that, okay, if we look at the pattern of fermions in a single generation of the standard model, but we, instead of specifying their usual U1 hypercharges here, we leave those as free variables, and now we ask how constrained they are by the anomalies, then it turns out that anomaly cancellation ends up implying that those 5 numbers, there's only 2 solutions, one of which is the actual physical one we see in nature, and then there's a second weird solution which is not the one we see. But the point is, it's very constraining. It almost completely determines the pattern of hypercharges in the standard model just from the fact that the anomalies have to cancel. Okay, but as I mentioned before, these traditional anomalies all cancel generation by generation. Each generation has its anomalies cancel separately, so you don't need, it doesn't give you any information about why there's 3 generations in the standard model, because there's multiple generations are not needed to cancel against one another. They all just cancel separately. So why 3 generations? Well, we had a new thing we noticed about this, which is that there's another kind of local symmetry that you might be interested in, which is local scale invariance, or in other words, Weyl invariance. So this is when the theory is symmetric under sending the metric g mu nu of x to an arbitrary conformal factor omega squared of x times the original metric. So ever since the discovery of general relativity by Einstein, various people, especially Weyl, Dirac, and Dickey in the early days, and then 't Hooft more recently, have argued that Weyl invariance really should be a symmetry of nature, that it's basically hard to imagine that the universe satisfies Einstein's general covariance but does not also satisfy Weyl invariance. Because, I mean, one way to say it is that, general covariance is the idea that that the choice of reference frame in which you're going to describe physics, it's just a choice of, it's not physical, it's just a choice of how you're going to describe what's physically going on. And moreover, it's a local choice. So if we choose a reference frame here on Earth in order to describe what's going on, that should not restrict the choice made by an alien in the Andromeda galaxy. They could choose a different reference frame to describe the physics in Andromeda. So fine. So then there's a similar question about choice of units. Weyl invariance is really a question about whether the choice of units is a local choice as well. That also seems like something where it's not really about the physics, it's just about how you're describing the physics. So it's just so it's very seems like it should be very much on a par with general covariance, the choice of what reference frame you use. So in particular, here on Earth, if I have 3 different sticks in front of me of 3 different lengths, a short, medium, and long stick, and I choose the one in the middle and I hold it up and I say, "Behold, this is the meter stick." This is the stick I'm going to measure all distances with here on Earth, relative to. An alien in the Andromeda galaxy, if they have 3 sticks in front of them, they should be able to independently choose which stick is the meter in the Andromeda galaxy if Weyl invariance is a symmetry. My choice here on Earth shouldn't determine which meter stick they choose in Andromeda. But in general relativity, as it's usually formulated, it does. Now, there's a famous trick called the Stuckelberg trick to reformulate general relativity in a way that classically is Weyl invariant. Classically allows Earth and Andromeda to choose different local meter sticks. But classically it becomes a symmetry, but quantum mechanically it appears to be anomalous. Or we have to ask whether it's anomalous. So let's think about it can be anomalous. So let's ask about now in the standard model, can it be a symmetry or not? Well, interestingly, if we ignore the Higgs field in the standard model, then the standard model classically is Weyl invariant. But still, at the quantum level, it looks like that Weyl symmetry has an anomaly. There's this famous formula for the trace of T, the stress tensor, which has to vanish if the theory has vanishing Weyl anomaly. But instead, it's famously given by this formula that on a curved spacetime, it's equal to a dimensionless coefficient C times the square of the Weyl curvature plus another dimensionless coefficient A times the Euler density, the Gauss-Bonnet curvature, where these dimensionless coefficients A and C just depend on the number of scalar fields, spin 0 fields, spin 1/2 fermion fields, and spin 1 gauge bosons in the theory. And the main point is that you notice that all of the coefficients in this expression are positive. So A and C appear to both be just positive numbers. They can't be 0, and so it looks like the anomaly is a non-zero value, and it looks like you just have a Weyl anomaly in the standard model. But in brief, what we noticed is that there are these, we noticed a way to cancel the anomaly using dimension 0 scalar fields, conformally coupled scalar fields. So it turns out there's 2 different ways to conformally couple a scalar field in 4 dimensions. There is the more well-known way, where the scalar field has a Lagrangian like this, where delta 2 is the unique conformally invariant second order operator, differential operator. But there's a second way where in using this delta 4, which is the unique fourth order conformally invariant differential operator. So in this case, the scalar field has mass dimension 1, but in this case, the scalar field has mass dimension 0. Okay, so in short, you can come back to this formula for the Weyl anomaly coefficients A and C. And also, I've also now added the expression for the vacuum energy per mode. And you can ask how these dimension 0 scalar fields change the answer. And we calculated this. It turned out that actually Fradkin and Zeitlin had already calculated it back in 1985. And the answer is that you get these new terms, which now depend on n0, the number n0 prime, which is the number of these new dimension 0 scalar fields. And you notice that they come with a minus sign in the expressions for A and C. And so we can ask, how many dimension 0 scalar fields would it take to cancel this first coefficient A in the standard model? It turns out 36 does the trick. But then, surprisingly, you notice, 36 also cancels this coefficient. Oh, and it also cancels the vacuum energy. So this is the thing we noticed. That actually, to state it a little bit more generally, it turns out there's this is the unique solution that makes both terms in the Weyl anomaly and the vacuum energy cancel. This is for a general, now I'm just letting there be a general number of spin, not for the standard model yet, I'm just saying, for the general Yang-Mills theory with this many spin 1/2 fields, with an arbitrary number of spin 1/2 fields, spin 1 gauge bosons, ordinary spin 0 scalar fields, and these new dimension 0 scalar fields. And the interesting thing is that in order for the vacuum energy and both terms in the Weyl anomaly to cancel, you find that the number of spin 1/2 fermions has to be 4 times the number of gauge bosons, which is exactly what is the case in the standard model. In the standard model, the number of gauge bosons is 12, and the number of spin 1/2 scalar fields is 48. But that's in 3 generations. So this 16 is the number of fermions in a single generation if you include the right-handed neutrino. So this cancellation requires us to include right-handed neutrinos, but it also requires 3 copies of the three generations. It doesn't work for 1 or 2 or 4. It only works for 3 generations. So it also, interestingly, it also requires that the number of ordinary scalar fields has to be 0. So it's basically saying that the Higgs field that we observe, apparently, if this cancellation is on the right track, is not a fundamental field in the theory. It's a composite or some sort of emergent field, which of course is interesting because many people over the years have speculated that already for many different reasons. Just as the last thing to say, as the last slide. So these new dimension zeros. Yes.
Question.
Yes.
So how about the observed Higgs particle already given the Nobel Prize? What's the comment about this when you say N00?
Exactly. So that's what I'm saying. So that has to. So if this is on the right track, apparently that is not a fundamental field in the theory. That is some sort of emergent or composite field. So how exactly that works, we're still trying to think through. We actually have a thought about it that we're working on, and there was a paper a couple of weeks ago by a follow-up to our paper by Volovic and collaborators claiming to have a explanation of this point, although I don't know if I agree with their paper yet or not. But yeah, that somehow the idea would be that the Higgs, as has often been speculated, is not a fundamental field that appears in the but that it's a composite of the other scalars and fermions in the theory.
Excuse me, how about this N0 prime? So that's fundamental, right? You need a 36 fundamental scalars.
Yeah.
I see. So the dimension zero scalar field.
Exactly.
Okay.
And so just as a last comment, the 2 interesting things to say about these dimension 0 scalar fields is that unlike ordinary scalar fields, which do not have a scale-invariant spectrum, like the Higgs does not have a scale-invariant spectrum, these dimension 0 scalar fields automatically do have a scale-invariant spectrum, just like the perturbations that we see in the early universe. So in inflation, the inflaton is normally an ordinary scalar field, and it doesn't have the right spectrum, so you have to put it in an accelerating background, an inflating background, in order to stretch the spectrum out to make it more scale invariant to match observations. But these scalar fields just automatically have the right spectrum already in flat space-time. They have it in any FRW universe, because any FRW universe is conformal to flat space-time, and these fields are conformally invariant. Yeah, they seem tailor-made to explain the primordial scale-invariant perturbations that we see in the early universe without having to invoke any period of inflation to modify their spectrum. And then another important thing about them, which is not really something that we first pointed out, so these scalar fields, a number of people there have been a number of papers. There's a kind of long past history about how to consistently quantize these fields. It's a bit like the Dirac-Lagrangian, where at first glance the Dirac-Lagrangian looks like it has unbounded energy, unbounded above and below, but you realize, oh, there's another quantization scheme that where you use anti-commutators instead of commutators, canonical commutation relations. You use anti-commutation relations and Pauli exclusion, etc., and you get a consistent quantization of the theory. So these dimension zero scalar fields, there's a similar story that people have found that there is a good quantization for these fields. And it's been more generally applied to a more general class of theories called Pais-Uhlenbeck fields. But these conformally invariant model dimension scalar fields are a special case of the Pais-Uhlenbeck field. The interesting thing is that in that special case, people have shown how to quantize the Pais-Uhlenbeck oscillator in such a way that the spectrum is, the Hamiltonian has all positive energy eigenstates, and all the energy eigenstates are positive and have positive norm. But in this limit, in this special case corresponding to the conformally invariant version that we're interested in, it's still the case that all the eigenstates have positive energy, but actually now the ground state has positive norm, but all of the higher energy eigenstates turn out to have zero norm. Their norms go to zero. They become null. So it smells like maybe there's some symmetry that we haven't totally understood yet, that maybe we're supposed to mod out these states, and maybe only the ground state is the only physical one. So we don't really understand this point yet. It seems maybe like it's hinting at the fact that maybe these scalar fields are not really new dynamical degrees of freedom. They don't actually add new particles to the theory. They're just kind of fixing the vacuum. They're fixing the Weyl invariance, the vacuum energy, the primordial vacuum perturbations, correlations in the primordial vacuum that are observed, but not actually adding any new. So you mentioned that we add these 36 fields, but we're not sure that we're actually adding 36 physical degrees of freedom. It seems to be more like an accounting trick, which is needed to fix various properties of the standard model vacuum. Okay, so with that, let me end. This is the summary. I guess I'll let you read it, but just part one was about looking back through the analytical extending back through the bang, and why that's a natural thing to do, and why it gives a nice new explanation for the dark matter. The second part was when you include the cosmological constant in the future, how it ends up giving new explanations for the arrow of time and for the observed homogeneity and isotropy and flatness of the universe. And then part three was about how there's this new cancellation mechanism, which on the one hand makes the universe Weyl invariant, which is good because the Big Bang seems to be a purely Weyl singularity. It's only really a singularity if you can Weyl transform it away. It's a bit like the horizon of a black hole. If you can make a coordinate transformation, you can remove the singularity of the horizon of a black hole. In a kind of analogous way, the Big Bang, if you have a Weyl invariant theory, it looks like the Big Bang is not really a singularity anymore. It can be Weyl transformed away. But then also these scalar fields, I forgot to mention that the reason they fit into this cosmological picture is that I guess I did briefly mention it, they seem to be necessary also to provide the observed spectrum of primordial density perturbations, the scale-invariant spectrum in the early universe. Okay, well, I apologize for running a little bit over, and thank you again for the opportunity to speak.
Thank you very much. Thank you, Latham. Question from the audience? I do have one, but I think the audience asked.
Can I ask one more question about this last part? So you mentioned there's a scalar field, but this scalar field is not a kind of a real physical scalar field, right?
So well, I don't feel very sure about that, but it seems to be that's what that seems to be kind of this hint that's my current understanding of. That's my current suspicion based on this fact that the non-ground states become null.
So you mean it could be like some ghost field from this regulation, or what kind of source could be this ghost field? So there's no kinetic term for this scalar field, right?
There is a kinetic. So it's Lagrangian is Lagrangian is given by this expression here. So you see the first term here. So whereas the ordinary kinetic term for a scalar field has minus box as the kinetic term, and then there's this plus 1/6 r to make it conformally invariant. Here, this guy involves box squared, so it's a fourth order differential operator. So it's a kinetic term, but it's an unusual kinetic term in that it involves 4 derivatives instead of 2. So that should ring alarm bells. That's what I think I didn't have it. I think I was rushing, so I didn't have a chance to explain this properly. But normally in relativistic field theory, if you have a Lagrangian with more than 2 derivatives, you worry that it's a sick Lagrangian because it would have ghosts, meaning that it would define a non-unitary quantum theory. But this Lagrangian happens to be in a class. In general, that's true. But this Lagrangian happens to be in a class, this Pais-Uhlenbeck class, where it's known that there is an that's what I was saying. It's analogous to the Dirac Lagrangian, where there's a couple, with the Dirac Lagrangian, there's a couple signs you flip here and there, and then everything is kosher. Same here, that if you try to follow the naive quantization prescription for this Lagrangian, it has negative norm states, ghost states. But there's this other quantization prescription that there's a good paper by Bender and Mannheim. There's another more recent one by Salvio and Strumia. Using so-called Pauli-Dirac, but it was really Dirac and Pauli who had originally pointed out that there's this other quantization procedure where you take certain variables to be anti-Hermitian rather than Hermitian. And anyway, that turns out to be how you make sense of this Lagrangian. So anyway, so it does have a kinetic term. It just turns out to be that when you use this alternate quantization prescription and you go to this special case of the Pais-Uhlenbeck oscillator, which is conformally invariant, that all of the non-ground states become null in the Hilbert space, and there's a question of what exactly how that is to be interpreted, which I don't feel sure about. It's a mystery at the moment. Yes, I see.
Let me make a comment. Is this the dimension 0 scalar can be also like axion type of a field, right? Axion, which can be dimension 0.
Oh, axion. Oh, yeah. Axion.
Yeah, axion. Yeah. Axion.
Yes. So that's true. Yeah. The axion doesn't have this same Lagrangian, but indeed it can be. It can be a dimension 0 scalar field, yeah. That's true.
Yeah, it does not have this type of kinetic terms, but it's dimension 0, yeah, excellent. And another comment is that some of the fractal model can have the false derivative powers x on the scalar, which I know for sure, and I also work on that. But the difference is that I think the Lagrangian term will also have a, I think it's, let me see. Actually, yeah, they are false derivative, like partial to the power false, the derivative to the power false on the scalar. But I think the terms actually also involve several scalars even on a single term. It's like a phi, d mu, d nu, phi, and a lot of terms, and then square of that term, that type of things. I'm not sure counting for the dimension. I think it's still, yeah, dimension 0, still dimension 0, except the kinetic term looks different. But anyway, I'm not sure the relative. I just make a comment. Yeah, so axion has dimension 0, and some of the fractal model has dimension 0 field. Oh, okay. Also, question from Hong.
I have a question about the Higgs boson. I mean the mass correction for Higgs bosons. Do you think that this mechanism for this new field here can handle that problem? You know, the quadratic divergence.
In other words, would it help with the hierarchy problem?
Yeah, that's right.
That's certainly a hope we have, but I don't think we have any. I mean, in general, one thing to say is that this is kind of only we don't have any concrete claims certainly to that effect, but we have a hope about that, and part of the reason for that is that, you know, so a normal free scalar field doesn't have any anomalous dimension, but famously in string theory, on the world sheet you have your the scalar fields living on the world sheet are dimensionless from the 2D perspective, and they do have an anomalous dimension, and so you end up building the dimensionful, fields in target space, like the various target space fields of the theory, by vertex operator, by exponentiating the world sheet fields, the dimensionless world sheet fields, and using their anomalous dimension to turn them into dimensionful fields. So I think we are thinking about whether something similar can be done here. Similarly, now we're not in 2D anymore, but we're now in 4D. But now again, these fields are dimensionless again. They are going to have an anomalous dimension, unlike an ordinary free scalar field. And so we want to build, exponential of these fields, a vertex operator-like construction. Maybe we can use to build the ordinary Higgs field or something like that. And I just think that in that approach, the counting, the kind of normal effective field theory arguments and counting of dimensions, and which go into the normal hierarchy, probably are modified, and I hope they're modified in the good direction.
Thank you. But the reason I ask is that in 1995, William Bardeen proposed to use scale invariant to help with the hierarchy problem.
That's
right?
true too. Yes, that I should have said that actually. That's actually quite true. In general, another reason for hope is that this whole idea of kind of making scale invariance a bigger part of the story, like you say, it has this whole back history that people have hoped, and Bardeen William Bardeen in particular had this idea that could be used to protect the lightness of the Higgs. That's another thing that would be great to connect with. But yeah.
Thank you.
Could you show again the precise way you obtain the formula for those number of the spin 0, spin 1 fields? Just exactly which constraint you solve. Is that the only solution? For example, suppose there could be other contribution, maybe for supersymmetric theory. Does that also modify the equations? For example, there could be spin 3½ or some other thing. Yeah.
That's a good question. A famous fact is that in ordinary supergravity, meaning just the supersymmetric version of ordinary Einstein gravity, the gravitinos, the spin 3½ particles which appear there, also appear with a negative contribution in these formulas. So there's like some negative number, I forget what it is, times the number of 3½ fields here, and negative number times the number of 3½ fields here. And so for certain very highly supersymmetric supergravity theories, it's also known that you get the anomaly cancellation. So I think it's only for theories that have more than n equals 4 supersymmetry, n equals 4 or higher supersymmetry. So, but that's that's so that's a good point. That the earlier story was that the way to get the anomaly, the only sort of places where the anomaly canceled were in these very highly supersymmetric theories. So this is a different way to that. But you're absolutely right that adding gravitinos is another way to do it.
Oh, so the graviton itself has no contribution, right? Here, there's no spin 2 particle in this form.
Oh, is this Shengcheng Gu?
Oh yeah.
Hi, nice to see you. So say that again. Sorry.
Oh yeah. I'm asking, how about this graviton? The usual graviton, does it also contribute to this anomaly cancellation?
Yeah, that's a good question too. So when you make the graviton, so the thing which I'm showing here is the normal anomaly cancellation people do is on a fixed non-dynamical background is the field theory living on that background Weyl invariant. And what I've shown is that the standard model on a non-dynamical background can be made Weyl invariant. Then there is this important question of then how should it properly be coupled to gravity in a way to preserve that fact. So indeed, in particular, if you take ordinary Einstein gravity, I mean, this is indeed a very, very, very good point. There's famously controversy about what the gravitational contribution is to this formula if you make the graviton dynamical, and different people disagree about the coefficient, and there's a kind of long running argument which has never been resolved in the literature about what the coefficient is. So I don't really even know the answer to that question very definitively, as opposed to these other coefficients that for the spin 0, 1/2, and 1, which everybody can agree on. The graviton contribution people disagree on. I think about it in analogy to, really what we've also shown is just that the global trace anomaly vanishes for the standard model when you add these 36 scalars. So I think of it as analogous to, if you want to take a global symmetry and promote it to a gauge symmetry, you first have to make sure that the global symmetry is anomaly free. And so here this is kind of the way I think about what's going on. This is saying like the global scale anomaly, the global trace anomaly vanishes if you add these 36 scalar fields. So it looks consistent to then turn it into a gauge symmetry, a local Weyl symmetry. Although so that's as far as I go at the moment. There is this important question of what's the right way to couple that to gravity in such a way as to preserve. What's a consistent way to couple that to gravity, basically, once you want to make gravity dynamical? I kind of suspect that Einstein gravity, just like the Higgs field is emergent, I kind of suspect that Einstein gravity and the Higgs field both arise from spontaneous breaking of local Weyl symmetry, or some maybe larger symmetry that includes Weyl symmetry. Yeah. Yeah, because Weyl symmetry is clearly spontaneously broken. I've kind of been imagining that the Higgs and Einstein gravity, which does not on its own appear Weyl symmetric, are things which reflect the appearance of the world after spontaneous breaking of this symmetry. Because they both don't seem to respect it. But how exactly that works, or what is cause and what's effect, is not clear to me yet. I don't know. Do you have any thought about that, Cheng?
Yeah, I think maybe you and you first.
I think the calculation here is the non-dynamical background, so graviton shouldn't take into account in the formula. It's a background geometry probes, right? As Latham say.
I mean,
yeah, but in this, sorry, yeah, in this supersymmetric case, if there's a spin 3/2 particle, naturally there should be graviton, right? So because in order to preserve supersymmetry, they appear together.
Yes, that's true too. The cancellation which works in supergravity involves you work on a it's like probe fields on a nearly flat background or on an ADS background, and Indeed, the cancellation involves not only a gravitino contribution, but a graviton contribution, and then the cancellation only works if you take one group's answer. You know, again, I said there's this controversy about what the coefficient of N2 should be, but there's one there's one possibility which has in its favor that it makes these highly supersymmetric theories, their trace anomalies cancel. So that's always made people suspect that that's probably the right answer for N2, but as I say, that it doesn't seem. I think none of the calculations are gauge invariant, and the problem is different people choose different gauges and get different answers.
But yeah, I do follow up. But for this formula, the cancellation, you try to assume is A equal to 0, C equal to 0, and EK equal to 0, or what? What exactly is the constraint to solve the value of n0, n half, n1? What is the conditions you impose?
So exactly, A equals 0, C equals 0, and EK equals 0. Exactly. In this equation has this solution. This equation down here is the solution. That's the unique solution of those three equations. This one down here is just the usual fact that each mode by mode that each scalar contributes h bar omega over 2, and fermion contributes minus twice that because it has two polarizations, and graviton has that all the bosons and fermions contribute either minus 1/2 minus or plus h bar omega over 2 times the number of degrees of freedom they have.
Sorry, why is the coefficient for fermions -2? And why is the other spin 0 for the dimension 0 spin 0 field is also 2?
Well, this is like in super. This is a famous fact that the ground state energy of the fermion is minus the fermion is minus 1/2 h bar omega rather than plus per degree of freedom, which is coming from the fact that the creation and annihilation operators anti-commute rather than commuting. I mean, they satisfy anti-commutation relations, I should say, rather than commutation relations. The fact that there's a 2 here for this scalar field is coming from the fact that it's a four derivative Lagrangian. So in the normal quantization scheme, you break it into two derivative. You can rewrite it as two derivative Lagrangians. So it's like really two scalar fields with two. It can be reinterpreted as two derivative scalars.
Mm-hmm. Thank you. But I wonder whether those conditions you use, if people also check maybe Green-Schwarz mechanism, do they also use similar things in the past for those conditions? Maybe just didn't apply to standard model. Are these conditions used in some other ways, I suppose? Do they also impose A equal to 0, C equal to 0, and EK equal to 0 for other theorem, as far as you know?
I don't, not as far as I don't think so. I mean, it is true that you know, what happens in string theory is that you demand that the world sheet theory, which is in 2 dimensions, is conformally invariant. And there's a lot more conformal symmetry in 2 dimensions than in 4. And you know, conformal group is an infinite group in 2 dimensions. So it ends up implying these conditions on the target space fields in the theory that they apply, that they satisfy the Einstein equation, etc. So it ends up, it's a different story. It's a different story, I think. I mean, it's not totally unrelated, but I don't think, as far as I'm aware, nothing like these dimension zero scalar fields play a role there. Although the target space fields are dimension zero scalar fields from the world sheet perspective again. So there is this there is that analogy. The targets, the coordinates, I mean.
Mm-hmm. Okay, thanks. Any other questions from the audience? So if not, I think we should thank Nathan again for the interesting discussion and the seminar. Thank you very much.
Okay, thank you.